Okay, welcome to lecture 7, crystal structure of metals. Today we're going to talk about different types of crystals that is seen in the metallic structure and their classifications, as well as how a metal crystal forms. We'll also look at that and at the end actually. And okay, let's start. So what is crystal structure? Can anybody say? What does it mean by crystal structure?
Sir,
Anyone?
the arrangement of atoms.
Yep, in one way we can say that the arrangement of atoms inside the metal or non-metals, whatever it is, and how the atoms are organized in the crystals of any metal or alloys. Okay, and to study that, first we need to know the chemical elements that a metal contains, or how we can distinguish the chemical elements. And we can actually classify the chemical elements into three groups. First one is the metal, which is solid. We have already talked about this. It contains luster, high reflectivity of light. It can be deformed plastically, and relatively high thermal and electrical conductivity. And in solid state, they exist in the form of crystals. And second one is the metalloid, which resembles metal in some respect, but in other respect it's not metal. Have some conductivity, but very little or no plasticity. And the examples can be like carbon, bronze, silicon, etc. And finally, non-metals, remaining elements are non-metals. That means all the chemical elements have been classified in here. And the next is, since we are going to study the atomic structure or crystal structure of a metal, so we need to have a clear understanding of how metals are bonded together, or chemical elements are bonded. So there are a few bonds that we need to talk about. First one is atomic bonding. I think you already know about this sort of bondings, because in your higher secondary education you have studied them. And I'll just go briefly. Atomic bonding, actually, four possible types of bonds can be seen in the materials. First one is the ionic. This is a very common bonding. The electron structure of atoms is relatively stable when the outer shells contain 8 electrons. We all know that if the outer shell of an atom contains eight electrons, then it is very stable. And there is a tendency of the material to make the outer shell contain 8 electrons, and that's how the ionic bomb actually forms, because of the attraction. Uh, One of the example is here, like sodium contains only one electron in the outer shell of it, but in the chlorine there is a lack of one electron on the outer shell, and that's why chlorine attracts. The sodium has the tendency to release that electron, and the chlorine has a tendency to take the electron from somebody else to make the outer shell the possible 8 electrons. And the sodium and chlorine both has the 8 electrons on their outer shell, but since sodium has given up one electron and it has become the positive ion, and the chlorine becomes negative. And there is a strong attraction between this positively charged and negatively charged chlorine and positively charged sodium, and that's why they form a very strong bonding. The bonding is so strong that the physical or chemical or properties, almost all the properties of individual element is gone. Like sodium, when sodium and chlorine produces sodium chloride, and sodium chloride is completely different from the sodium and chlorine. Okay. And they produces a completely different properties. And that's the significance of ionic bond. It actually produces a different type of material. Okay. And the second one is the covalent bond, mostly seen in the gaseous structures, gaseous molecules. It is actually the sharing of electrons of the outer shell. Okay, the hydrogen, the example showing in here, the electron from hydrogen comes close to the carbon outer shell, and then they share the electrons. And because of that sharing, they produces a bond between carbon and hydrogen to produce methane, and that's called the covalent bond. It's basically the sharing of electrons of the outer shell. The third one that we need to really understand, this one is the metallic bond, because we're going to study the crystal structure of metals. So what is the background in here? The background is the metallic structure has the lack of oppositely charged ion, because if it is aluminum, everything is aluminum. So there is no other negatively charged ions present in the metallic structure. And the second one is the lack of sufficient valence electron to form a true covalent bond. Because as you know, the metal has the outer shell. Outer shell contains like from 1 to 3, 4 electrons. So there is not sufficient electron to produce covalent bond between the molecules. And that's why the sharing of valence electron by more than 2 atoms occur between the sharing of electron. Instead of happening it between 2 atoms, it actually happens, the sharing occurs between all adjacent atoms, or that means the more than 2 atoms can share the outer shell electron that that contained by the metallic atoms. And each atom contributes its valence electron to form an electron cloud. That means the atoms that are present in the metallic structure, they releases their outer shell electron, and that electron, those electron actually produces a electron cloud that moves around the metallic structure. And every atom actually shares those electrons whenever they need them. Okay, and these electrons actually freely moves around on the material, and that is the reason why the metals show high conductivity of either thermal conductivity or electrical conductivity, because of those free electrons moving around through the structure or through the metallic structure. And the metallic ions, why the ions stay together? Actually, they stay together because of the mutual attraction between the negative, for the negative electron cloud. They all want to share the electrons. They all want to have the electrons on their outer shell. And that is why they stay together. The atoms stay together and produces a very strong bond. Okay, and that is how the metallic bond forms. It's basically, if we talk about the summary is all the atoms release their outer shell electron, and the electron cloud is formed, and that electron cloud is shared by all the atoms. Okay, and that's how, and because of the attraction to the electrons, all the atoms stay together. And the final one is the very weak bond, which is van der Waals. This type of bond occurs naturally for gaseous elements. And when the atoms are brought close together, they actually forms 2 poles, positively charged and negatively charged poles, because of their outer shell electron. And because of that positive and negative pole, there is attraction between the electron and the positive charge, and that attraction actually creates the van der Waals attraction. That is called the van der Waals attraction, and that actually creates the bonding between the elements. It's a very weak bond between the positive and negative centers. Okay, do you have any question? right. So now we are going to go to the crystal structure, talk about crystal structure. And what is the space? There's a common term, it's called space lattice. And what is the space lattice? Space lattice is a three-dimensional imaginary lines connecting the atoms. It's called space lattice. That is how actually if you talk about it more generally, it's like how the atoms are organized in a metallic structure. It's called the space lattice. And the space lattice is huge. Okay, if you, it's a huge structure containing billions of atoms on the space lattice. But these atoms are organized in such a way that if you extract a certain portion of that space lattice, which contains all the symmetry, actually symmetry on all the faces of that, is called the unit cell. If from a crystal lattice, you take a certain portion, which actually, if you repeat that portion in all the direction, then you will get the space lattice. And that unit cell, that is called the unit cell, and that unit cell actually contains all the properties that the space lattice might show. Okay, that is why we need to study the unit cells. Okay. If you repeat a unit cell in all the directions, you will get the space lattice. And in the case of a space lattice, how do we denote, describe a space unit cell? Okay. To describe the unit cell, there is a certain standard, and that standard says that the edges of the unit cell will be denoted as A, B, and C. A is along the x-axis, B is along the y-axis, and C is along the z-axis. Okay, it will not be like always along the z-axis or along the x-axis or y-axis. Okay, because the unit cell is not always right angle. Okay, it's not always like a cube. It can be different. And the angle between the edges, actually between the edges like B and C edges, the angle is called alpha, and the angle between A and C is called beta, and angle between A and B is gamma. And these are the things, A, B, C, alpha, beta, and gamma. This actually defines how a unit cell will look like. Okay. And there are 14 possible type of space lattices, and they can be classified into 7 crystal groups, which is shown in here, like cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. These are the 7 crystal systems, and these 7 crystal systems actually are more sub-classified, like cubic crystal system can be classified into 3 groups. One is simple cubic, face-centered cubic, body-centered cubic. There are 3 types of lattices present in the case of cubic, and tetragonal has 2 types, orthorhombic has 4 types, rhombohedra, hexagonal only 1 type, monoclinic there are 2 types of monoclinic crystal system, and triclinic is 1. Okay, and this unit cell can be described with the length of edges and the angle between the edges. Okay, and for example, the cubic cell has contained like the edges which are equal. A, B, C, all 3 edges are equal, and the angle between those edges are also 90 degree. Okay, that's how the cubic cells are formed. It's a cube actually. And for the tetragonal, A and B are the same, but C, the height would be different. The C will be different. It can be smaller than AB, or it can be larger than A and B. And the angle between all of them is 90 degree. Okay, that means the angle between AB, AS, and angle between BC and angle between AC are 90 degree. There, that means it is a square-based right prism. Okay, and there are 2 types of lattice in there. And similarly, all other crystal systems can also be described using the length of edges and the angle between the edges. In unit cell, basically there are 2 types. One is called primitive, and another one is non-primitive unit cell. The primitive unit cells only contains corner atoms, there will be only corner atoms. There will be no atoms present in the inside the unit cell. And but in the non-primitive unit cells, the atom can be in the faces of the unit cell as well as interiors. In metals, we usually see three types of crystal lattices, common lattices. Those are body-centered cubic, face-centered cubic. The body-centered cubic and face-centered cubic are actually the cubic lattice that we talked about. Our C crystal system is cubic. It has three lattices: body-centered, face-centered, and simple cubic. And in the metallic structure, there is body-centered cubic and face-centered cubic, and another one is the hexagonal closed pack. Okay. These three types of lattices are mostly observed in the metallic structure. Either it can be metal or alloy. So for the body-centered cubic, in the case of body-centered cubic, there are four atoms, there are 8 atoms around, and in the four corners there will be atom, but if you make it an unit cell, each corner will contain 1/8 of an atom. The fraction will be like 1/8, and there is 8 corners, so the number of atoms in the corners of an unit cell of the body-centered cubic unit cell will contain will produce 2 atoms in 1 atom in total, and there will be another atom at the center of the unit cell, and that will total number of atoms will be there, like 2 atoms will be present in the body-centered cubic structure. And the examples of body-centered cubic structure would be like iron, chromium, tungsten, molybdenum. And you cannot actually say the iron, though the iron actually exists in the room temperature. They can be in the body-centered cubic, but sometimes they can change their phases. Sometimes iron can become face-centered cubic, and then it can be transformed into body-centered cubic. And for the body-centered cubic, face-centered cubic structure, the corners will have 1 atom. In total, corners will have 1 atom, and each face will contain half of the atoms. Okay, and if there is since there is 6 faces, the total number of atoms will be like 4 atoms in the face-centered cubic structure. And the examples are like aluminum, nickel, copper, gold, silver, and also you can say like gamma iron, which contains face-centered cubic structure. We'll talk about those actually, and the delta iron, gamma iron, and alpha iron. There are 3 types of iron can be produced depending on the temperature, what temperature you are treating that one. The comparison is very simple. It's like there are 4 atoms are similar, but body-centered cubic actually contains one single internal atom, and face-centered cubic contains 2 internal atoms, which actually stays on the surface on the each faces of the unit cell. Half of the atom is present in the unit cell, and the metals with face-centered cubic lattice are ductile and good conductor because face-centered cubic has more packing density, as well as there will be more electrons present on the face-centered cubic structure, and it will also show the higher density, and that is why the face-centered lattice actually shows good conductivity as well as ductility. Hexagonal closed pack, it actually has 2 basal planes in the form of hexagon with an atom at each corner and 1 atom at the center. Actually, we need to see the images in here. There are 7 atoms at the top, and there are 7 atoms at the bottom, and there will be 3 atoms in another plane at the midpoint, and 3 atoms will be like whole atoms, and each corner atoms will be shared by the 6 adjacent unit cell. So each corner atom, we can represent it as 1/6 of an atom, and the middle atom actually shared by another only 1 unit cell, and that is why there will be half atoms. Okay. And the total number of atoms in the closed pack hexagonal will be like 6 atoms. And the examples are like magnesium, zinc, and cadmium. Okay. Okay, so for the atomic radius for body-centered cubic structure, how do you calculate the atomic radius of body-centered cubic structure? In this case, if you consider the 3 atoms at the through the diagonal of the cube, and the length of the diagonal can be termed as BD, and the height is one edge of height is A, and the diagonal FD. Okay, if you consider this, the base diagonal is like FD, then we can say like BD square equals to, since this is the right angle, since we know that the cubic unit cells have 90-degree angles between the edges, so we can say like BD square equals to FD square plus A square. And since FD is also a diagonal which contains a length like, here if we consider this is also a right angle triangle. So this is A and this one is also A. So we can say like 2A square. A square plus A square, FD square equals to A square plus A square. So we can say like 2A square, and then we can find like BD equals to root over 3A, which is equals to 4R, and then we can say like the atomic radius R will be, since how do we get the 4R? 4R is actually the length of this, because this atom, this one is 1R, this one is 2R, and this one is 1R. So there is 4R length of BD. So we can say that root over 3A equals to 4R, then R will be root over 3A divided by 4. This is the atomic radius of, can be found using the unit cell. If you can find the unit cell, then you can get the atomic radius. You can find the atomic radius. And for the simple cubic and face-centered cubic, these are the self-studies. You can study them at home. It will be like similar way you can find the atomic radius. And the packing factor, how closely an atom a unit cell is packed. If you want to describe that, you use like atomic packing factor, and the atomic packing factor is the ratio of volume of atoms divided by volume of unit cell. That means the fraction of a volume of unit cell which contains the atom. That we know the volume of atoms will be like pi 4/3 pi r cube. R is this is the R, the atomic radius. This is the volume of a single atom. Okay, this is the volume of a single atom. Since body-centered cubic structure contains 2 single atoms, then you can say like the total volume of atoms are actually 2 and for volume of a single atoms, and then the volume of the unit cell will be like A cube. Okay, if we describe it using a 2-dimensional structure, then if there is atoms, like there are 2 atoms in this region, then the area of the unit cell will be like below, and the area of the atoms will be at the top. It's 2 atoms. So in the case of 3 dimension, we can consider like the volume of a single atom. Since there are 2 atoms, we multiply it by 2 and then divide it by the total volume of the unit cell. This is the packing factor of the body-centered cubic structure, which is 0.68. And self-study is simple cubic and face-centered cubic structure. Do you have any question?
Sir, A R equal to 4R কিভাবে হলো স্যার?
Which one? This one?
So root 3A equal to 4R.
How? Oh, you're asking like why root 3A equals to 4R, right?
Yes, sir.
Okay. Actually, the BD is equals to 4R. You got the root 3 from here. Okay. By solving this equation, BD equals to root 3, since A square and A square if you root it, then square is gone, then there will be A, and root 3 will be there. But BD, we can actually say the BD equals to 4R. How? BD actually the length from here to here. Okay, length from here to here is BD, this length. Am I right?
Yes,
Yes,
sir.
sir.
And this BD contains 3 atoms, right? Each atom is connected to each other. So this atom has 2R. Okay, if we divide it like this is 1R, this is 1R, this is 1R, and this is 1R. There are 4 R's. Am I right?
Yes, sir.
That's how we get actually the 4R. Got it?
Yes, sir. Thank you.
Okay. Any other question?
Sir, will we have a full set of questions from this topic?
Sorry.
স্যার আমাদের কি এই টপিকটা থেকে একটা ফুল সেট কোয়েশ্চেন আসতে পারে নাকি?
I don't think so. There might be one full question is 35 marks. I don't think there will be 35 marks from this lecture. Okay. And since this is actually already known knowledge, so there will not be much. But you need to study them because if we look at the previous year questions, there are questions that come from this section. Okay.
Yes, sir. Yes, sir.
স্যার আগের সেটটা থেকে কোশ্চেন আসতে পারে স্যার?
Sorry, আগের সেট বলতে কোনটা বোঝাচ্ছ?
স্যার আগে মানে স্যার আগে যেটা পড়ানো হলো স্যার, ওই যে ডিস্ট্রাকশন, নন ডিস্ট্রাকশন।
That means আগের 6টা লেকচারের কথা বলছো?
স্যার জি স্যার, ওইটা থেকে কয়টা সেট আসতে পারে স্যার?
সেট সম্পর্কে এখন মাথা ঘামানোর কোনো দরকার নাই। তোমরা পড়াশোনা করো, লেকচার যখন শেষ হয়ে যাবে তখন সেট সম্পর্কে আমি আইডিয়া দেব। ওকে
স্যার পার্কিং ফ্যাক্টরে স্যার 2 কেন গুণ হলো স্যার? 2টা কি জন্য?
পার্কিং ফ্যাক্টর না, প্যাকিং ফ্যাক্টর।
প্যাকিং, জি স্যার, প্যাকিং ফ্যাক্টর।
Okay, for the packing factor, if you talk, that's why I was showing this two-dimensional structure actually. If this is a unit cell, this structure is A, and this length is A, and this length is A, and the radius or diameter of these atoms are D. Okay, then how do you calculate that? How packed this area is? Okay. And to calculate that how packed this area is, we need to have the total area, which is A square, right? And the area of each atom. The one atom got area pi by 4 d square. This is the area of one atom. Then you need to multiply with 2, right?
জি স্যার।
And since we are talking about the volume, how closely the volume is packed, then we need to have the volume of a single atom, which is here. This is the volume of a single atom. And since the body-centered cubic structure contains the total number of atoms in the body-centered cubic structure is 2, then to get the atomic volume, you need to multiply it by 2.
জি স্যার।
Okay? And A cube is the total volume of the unit cell.
জি স্যার।
Okay, did you get it?
জি স্যার।
Okay, any other question? Okay, let's move to the next. Next is the density of lattice material. If you want to find the density of the material, then atomic density, then you can use like mass of the atoms and then the volume. And using the Avogadro number, you can calculate, Avogadro number n, you can calculate the volume, atomic weight, and Avogadro divided by Avogadro number, then you can get the total weight of the atom and then the volume of the atom. Okay, by doing this, you can find the density of the lattice material. Okay. Okay, so the next is, now we are moving to the crystal structure. There are some terms actually you need to know before going to the core of the crystal structure. The first one is the polymorphism and allotropy. What is the polymorphism? The polymorphism is the property of a material to exist more than one space lattice in the solid state. That means sometimes some material can stay in different, can produce actually the different crystal structure inside them. Sometimes it can be body-centered cubic and sometimes it can be face-centered cubic. Okay, it can change from body-centered cubic to face-centered cubic and then again face-centered cubic to body-centered cubic. Okay. And some material can interchange between them, between body-centered cubic to face-centered cubic, but some materials can't. Okay, so the phenomena is called the polymorphism. The property of those materials are called the polymorphism. If the material can exist in more than one type of crystal lattice in the solid state. Remember that it should be in the solid state. Okay. And if the change of the structure is reversible, that means if it can go to body-centered cubic and then come back to the face-centered cubic, that is the reversible change. And that because of that change, if change is reversible, then the polymorphic change, that polymorphism is called allotropy. Okay. That means if the change of crystal structure from one type of unit cell to another type of unit cell occurs, that is called polymorphism of that material. The property is called polymorphism. If that change is frequent, like it can is reversible. If you change, for example, the iron is staying at body-centered cubic structure, and then you changed it to face-centered cubic structure, it will not remain in the face-centered cubic structure forever. It will change back to body-centered cubic structure, and that is called the reversible change. And that property is called the allotropy. And iron is an allotropic material. Okay, if you change it to face-centered cubic, over the time it actually comes back to body-centered cubic. Okay, but it is polymorphism. Okay, that the changing of the crystal structure is the polymorphism, and there will be some most of the materials actually will not show this kind of property. Okay, there are 15 metals that show this type of properties, and iron is the best example. And iron actually crystallizes at 2800 degree Fahrenheit, and it is body-centered cubic. First, when liquid iron is solidified, it starts to solidify, it actually forms delta iron, and that is actually body-centered cubic structure. When the temperature drops to 2554, below 2554, it actually transforms into face-centered cubic structure, which is called gamma iron. And when the temperature decreases more at 1670 degree Fahrenheit, it again goes back to body-centered cubic structure, which is called alpha iron. Okay, and this is called the polymorphism. Okay. Next term is the crystallographic planes. The layer of atoms or the planes along which atoms are arranged are known as atomic or crystallographic planes. That means there will be certain orientation of the atomic organization. The atoms that organized in the crystal structure in such a way that it creates some planes. Okay, and the planes can be defined arbitrarily or sometimes, for example, if you look at this crystal structure in here, you can consider a plane like from this corner, that corner, and outer corner, that one and that one. You can define a plane any way. Okay, according to, in this plane, the atoms, organization of atoms could be different, will be different if you consider another plane like this. In this orientation, if you consider another plane like this, the atomic orientation actually changes if you define plane differently. And these planes are significant in such in a way that if you talk about the piezoelectric material, this plane is very important. If the piezoelectric property is better in this plane, and if you apply loading in this plane on this plane, then you will not get better piezoelectric effect. Okay, that is why the plane is also important, and the atoms that are organized the atomic organization in the plane is also important. And these are called the crystallographic planes. This can be defined with the Miller indices. Okay, this what is the plane? If you want to define a plane, and then you have to define it using Miller indices. And that plane is parallel to one plane. All the planes are the same. Okay, if you consider this plane and parallel to this plane, all the planes are defined with one single Miller indices. Whatever the distance from a certain point it is, the distance does not matter. The plane matters, and that plane is defined by the Miller indices. It can be any angle. I'll show you more in the coming slides. And to calculate the Miller indices, one corner of the unit cell is assumed to be the origin of the space. You can consider as a corner of an unit cell to be the origin of the unit cell space lattice or space coordinates. Any set of planes is identified by the reciprocal of its intersection with those coordinates. Okay, and then any set of planes you want to define is the intersection with those coordinates, or either on the x-axis or y-axis or z-axis. Okay, whatever you want to consider. If you want to consider a plane, then you have to find out the intersection points where the plane has intersected on the x-axis, y-axis, or z-axis. Okay, and I'll show you that if a plane is parallel to an axis, it intersects it at infinity. That means if you have a plane parallel to x-axis, let's say this is the x-axis, and you have a plane in here which is parallel to that, then the plane actually intersects on x-axis at infinity. Okay, that means that plane, this will be the parallel line, and parallel lines always intersect at infinity, and you have to consider that as infinity. So it will be more clear in here. For example, if you want to consider a plane like G is this one, and if you want to consider this plane, and this is the origin. Okay, this is the origin of the unit cell on the space lattice. Then how do you define this plane using the Miller indices? Okay, to define that, you have to consider where the plane has intersected in the x-axis, y-axis, and z-axis. So this plane is parallel to the x-axis. So we have to consider that this plane has intersected the x-axis at infinity. In the y-axis, this plane actually intersects at 1. That means since this is an unit cell. Okay, so it is 1 in here. It can be 0.5 of the unit cell. If you want to consider the plane in here at this point, then it can be 0.5. It can be 3 unit cells can also be considered for the sake of calculation. Okay, since we are considering just 1 unit cell, so the edges we are defining as 1. Okay, so this is the 1. So intersection is at 1, and in the y-axis, and in the z-axis, this plane is also parallel to the z-axis. So in the case of z-axis, the intersection point is infinity. And to find out the Miller indices, you need to get the reciprocal of the intersection point. The reciprocal of infinity is 1 over infinity, in the intersection 1 over 1, and 1 over infinity. And that gives you 0, 1, and 0. So the Miller indices for the plane, for this plane, is GB, this plane will be 0, 1, and 0. So all the planes parallel to this plane will be identified as 0, 1, 0. Okay, so all the planes parallel to this will be indicated as the Miller index 0, 1, 0. Now, if there is a plane which is in the negative side of the origin, you consider the origin in here and the plane is on this side. Okay, plane is on this side. Then what happens? Then in that case, you have to, this is in the negative side, then the index will be negative. And how do you define that? The negative index will be defined with a bar on top of it. Okay, to indicate the negative side of that origin. Okay, and the Miller indices results in fraction. Sometimes it can be fractions like 0, 1/3, 1. Okay, in that case, if it comes to because of the reciprocal, okay, sometimes it can be fractions. If it comes with the fraction, then you have to multiply with the bottom one. Okay, those fractions must be cleared. How do you clear it? Then you multiply with 3 to the all elements. Like 3 multiplied by 0 will be 0, and 3 multiplied by 1 over 3 will be 1, and 3 multiplied by 1 will be 3. That's how we define another plan. Now, to be more clear about the Miller indices, we need to investigate another plane. Okay, for example, if you want to consider this plane in here, this one, the plane can be in any orientation. Okay, if you consider this plane, then this plane has intersected on the x-axis at a distance 1. Let's write 1. That's the intersection. And in the y-axis, it intersects at 1. Y-axis intersects at 1. In the z-axis, it intersects halfway. Halfway. That means 1 over 2. 1 over 2. And how do you find the Miller indices? You divide it by 1 divided by 1. That means you do the reciprocal 1 divided by 1, and then 1 divided by half. That means there will be 2. So the finally it will be 1, 1, and 2. The Miller indices of this plane will be 1, 1, and 2. And that's how you can consider any different or any orientation you want, and then you can define that plane with the Miller indices. Okay, any question in here?
No, sir.
1 on 2 এর ব্যাপারটা একটু বলেন স্যার।
Which one?
1 on 2 যেটা আসলো আর কি, মানে ক্যালকুলেশনটা।
This one. Okay, this one is very similar to that. Okay, at first, if you want to, you need to define a plane like this one. You define a plane like this. Okay, and then you find the intersections. To find the intersection, where does this plane intersect in the x-axis? At this point, and this the length of this point from origin will be 1. So let's put the x intersection as 1, and the y intersection is also 1, and z intersection is 0.5. That means half. Okay, and you do the reciprocal. That means 1 over 1. You do the reciprocal 1 over 1, and you do the reciprocal 1 over 2. And finally, it becomes like 1, 1, and 2 goes to the up, and it becomes 2. Then you get the Miller indices 1, 1, and 2. Did you get it?
Yes, sir.
All right. So the mechanism of crystallization, how crystallization occurs. That means how a metal transforms from liquid to the solid state. It actually occurs in 2 stages. One is nuclei formation, and another one is crystal growth. Nuclei formation is the significant one, and then final crystal growth is very simple. Okay. In the case of a material at a very high temperature, at the melting point temperature, material is liquid. Okay, at higher than melting point temperature, material is liquid, and material actually contains kinetic energy and potential energy. What is the kinetic energy? Kinetic energy is associated with the vibration of the atoms, like how much speed the atoms have. It will define the kinetic energy. The higher the temperature, the kinetic energy will be higher, and the potential energy, actually the distance between the atoms. When you hit the material, the distance between atom actually increases because of the kinetic energy. Higher the kinetic energy, the distance between atom will also be higher. Okay, in that case, the potential energy will also be higher. So the kinetic energy is related to the speed of the atom, and the potential energy is related to the distance between the atoms. Greater the distance, and greater there will be the potential energy. Okay, and everything depends on the temperature. Okay, temperature and pressure. Because, since we are going to analyze all of this at room temperature, at normal pressure, so pressure variation is not considered in here. The kinetic energy and potential energy of the material will be dependent on only the temperature of the material. Higher the temperature, higher will be the kinetic and potential energy. So for the formation of nuclei, how nuclei actually forms. To form the nuclei, when the temperature decreases from a higher temperature than the melting point temperature, when the temperature decreases, kinetic energy decreases as well as the potential energy decreases. And because of this decrease in potential energy, atoms come close together and they starts to form a certain regular arrangement of the atoms. Initially, when the temperature is very high, greater than melting point temperature, then atoms are very much scattered. They don't have any regular structure. They are very much scattered and they moves randomly. But when the temperature decreases and comes close to the freezing point temperature, then what happens is that a group of atoms actually forms. Okay, there will be several group of atoms formed in the space lattice, and they will be organized. And sometimes they will organize and then they will break up, and then those atoms goes to the another group of atoms, and then they form another group. Okay, that's why the grouping occurs. Okay, and when the temperature is sufficiently low, these groups become stable. Okay, at different region of the structure. For example, if you have a container in here there will be a group become stabilized, and there is another group stabilized, there is another group become stabilized. When the group of atom become stabilized, they don't get separated from each other. These are called the nuclei, and that is called the nuclei formation. And that nuclei formation occurs because of the decrease in temperature. That means, in other words, we can say that the kinetic or potential and decrease in the potential energy of the atoms. And the nucleus contains a group of atoms. But initially, when temperature is very high, then there is no group. Atoms are independent; they move scatteredly in the region. Okay, and sometimes they form groups, and then groups break up. Some atoms come out of here and forms another group in here, and then again some atoms come out of here, forms another group in here, and at some point these groups become stabilized. No atoms come out of this group, and this group will be said as nuclei. Okay, this group will be called nucleus. Okay, and once the nucleus is formed, I'll come to this one later. Once the nucleuses are formed, this will be called the nucleus, and nucleuses form all over the region scatteredly at different places. Nucleuses will form, and once this is stable and temperature is further decreasing, temperature reaches the freezing point temperature, then more atoms starts to come and join the group. When the groups are formed, the atoms will come and join the group to grow. The atoms will come and join the existing groups, and sometimes the new groups will also be formed. New nucleus will also be formed. Okay, in that way, more atoms come to the new group, and then the crystal starts to grow. That means unit cell is formed, and then the crystal, more atoms coming to the crystal, and crystals become larger and larger and larger. Okay. And once the crystal become more larger, there will be liquid still in those places. And after that, when the individual crystal grow is complete at the boundary, how this boundary is formed? Because when the atom starts to organize, atom starts to get attached with the crystals, they can attach freely. Okay, they form regular structure. The crystals are regular structure, but when these crystals are formed, atoms are organized at the boundary. Atom cannot be organized regularly. The atoms that are organized in the crystal, those can be organized regularly, but when there is a very small space between the crystal, that in that small spaces, atom cannot organize regularly, and that's irregular arrangement of atoms at the boundary of the crystal actually forms the grain boundary, and the whole crystal is called the grain. And this boundary where the atoms are organized is not organized is called the grain boundary, and those grain boundary will be visible under the microscope. When we do the metallographic study, then we'll be able to see that there will be grain and there will be grain boundaries. Why do we see the grain boundaries? Because light is reflected from the crystal is different from the light is reflected from the grain boundary because of the irregular arrangement of the atoms. Okay, that is why the grain boundary actually appears as a black line in the microstructure. Okay, and do you have any question so far for the crystallization? No, if not, then we'll go to the cooling curve. This is called the cooling curve, how the cooling occurs. The coordinate of this cooling curve is the temperature and the time. With the increase of time, when you decrease the temperature, this is the very high temperature where the atoms are not regularly arranged. The atoms are individual and they move at a very high speed. They contain very high potential and the kinetic energy. When the temperature decreases and comes close to the cooling temperature, that means this is the freezing point temperature, okay, melting or freezing point temperature. When it comes close to freezing point temperature, then the nuclei forms, okay. The nuclei starts to form, they form and then they break up, they form and then they break up. When the temperature comes to the very close to the freezing point, then the nuclei become very stable and the crystal starts to grow at the freezing point temperature. And as we know, the phase change occurs at a constant temperature. That means temperature does not change. So when from the starting point of the nuclei formation, the whole up to the whole crystal growth, where the crystal will be grown, okay, there will be crystal. Up to the crystal growth, the temperature of the material will be constant, okay. But in actual case, the temperature remains constant. But in actual case, if you look at the very closely, then what will happen is that you will need some undercooling in the case of pure metal. And what is the undercooling? Undercooling is that when there is a crystal, when a crystal starts to form, there is an interface between this is the solid and there will be liquid. Okay, there will be liquid on the liquid metal and there will be crystal. And some energy is required when to form a surface between liquid and solid. Okay, and because of that energy, there will be the temperature loss. Okay, how does this energy? Where does this energy come from? That energy actually comes from the temperature. Okay, and because of that surface energy that is required between the to form a solid liquid interface, and that energy comes from the temperature, and then because of that energy, the temperature actually decreases. Okay, temperature decreases very slightly, not very much. There is a slight decrease in the temperature occurs, but once the crystallization is complete, that energy gets released again. And once that energy gets released, then the temperature goes up again. Temperature goes up again and moves to the freezing point temperature. And once the solidification is complete, the whole system has solidified and produced the crystals, and then the temperature starts to decrease in the solid state. Okay, did you understand the undercooling? The undercooling, the basic reason for undercooling is the energy required to form the surface between solid and liquid, the interface between solid and liquid due to the formation of crystal. And that energy, when the crystallization is complete, that energy again gets released. Okay, and that is because of that release, the temperature again goes up to the melting point temperature, and then that the cooling to the room temperature occurs. Okay, any question in here?
স্যার নিউক্লিয়ার ফর্ম হওয়ার পরে কি হলো স্যার, একটু আস্তে আস্তে বললে ভালো হতো স্যার একটু।
After the formation of nuclei, more atoms come in contact with the nuclei and get stabilized, and nucleus gets expanded. Okay, the nucleus gets expanded to form the crystal. Okay, and when the crystal starts growing, this will be the much easier. The nucleus will be formed and the more atoms will come in contact with those nucleus, and then it will get expanded. That means crystal will be larger. This will be the solid part. Okay, and the solid liquid interface that I was talking about is this is the crystal is solid and this is liquid. Okay, and when more atoms comes to close to the crystal, and then the crystal starts to grow. And when the crystal starts to grow larger and larger, and then there will be very small space remaining between the crystals, and that in that small space, atoms are organized discretely. Okay, there is no regular arrangement between the atoms, and these are called the grain boundary. And the crystals are called grain, and the irregular arrangement of the atom between the grains is called the grain boundary. Okay, that's what happens after the nucleation. Okay, any more question?
স্যার যেই টেম্পারেচারে ফ্রিজিং হওয়াটা শুরু হয় ওই টেম্পারেচার যে ফর্মটা হয় সবগুলো কি একই স্ট্রাকচার হয় যেহেতু টেম্পারেচারটা স্যার সেমই থাকে?
Yep, the structure is same because as you know, the metal, if you are cooling the iron, okay, from liquid to solid state, the iron will form body-centered cubic structure. So all the crystals or nucleus that are formed will be body-centered cubic structure. Did you ask this question, or did you mean anything else?
Yes sir, এটাই জিজ্ঞেস করতেছি।
Okay. All right, any other question? And the thing is that in the grain boundary, they will not maintain the unit cell, okay, because of the irregular arrangement of the atoms. This arrangement will be according to their space lattice or unit cell, but in here they will not follow that. I could not hear you. Did you ask like undercooling? When undercooling occurs?
Yes, sir.
I did not actually hear you.
Undercooling টা স্যার কেন করতেছে, কখন থেকে শুরু করতেছে?
No, we are not doing the undercooling. Undercooling is occurring simultaneously when the cooling occurs. That means when crystal starts to form in here, then there is a surface energy. Do you understand the surface tension?
স্যার নেট প্রবলেম ছিল স্যার, বুঝতে পারিনি স্যার।
Do you understand the surface tension? There is energy relevant to the surface tension, right? And whenever there is a solid and a liquid is present, there is a energy between the solid and liquid. Okay, and since it was in the completely liquid form from A to B, and suddenly it started forming solid, and there will be a energy consumption when a solid forms. And the surface between solid and liquid, because of the interface of surface between solid and liquid, there will be a temperature drop. Okay, because of the formation of the solid liquid interface, there will be a certain loss of energy, and that loss of energy is reflected with the decrease of temperature. There will be certain decrease of temperature, but when the crystallization is complete, then that energy again gets released, since there is no solid liquid interface anymore. Since there is no solid liquid interface anymore, so that energy gets released. Okay.
Yes sir.
Okay, next is the crystal imperfection. So why crystal imperfection occurs? Because sometimes when most of the crystal imperfection actually occurs at the grain boundaries, where there is no regular arrangement of atoms. Okay, this is the grain boundary. The crystal imperfection actually occurs in these regions. Okay, and if you do if the cooling of the material is not it's not slow, then also crystal imperfection can occur. Okay, and there are two types of crystal imperfection showing in here. One is vacancy, another one is interstitial. Vacancy means when the crystal starts to organize from this way, crystal is growing from all 4 ways, and the liquid is trapped in here. But at the end, you see that there is a lack of atom in here. There's no atom in this region, and that is blank. And that is why this is called vacancy. There is lack of atom. It's called the vacancy, and because of that vacancy, it is called it is a defect in the crystal. Okay, and sometimes there will be an excess atom. Okay, and because of that is excess atom or larger atom or impurity present in the crystal lattice, then it will behave like this. Okay, larger atom is present in the crystal lattice. That is called the interstitial, okay, crystal defect. And another one is called edge dislocation. This is called edge dislocation. That means crystals are organized from this side and that side, but suddenly there is another plane of atom comes in here. Okay, and the imperfection occurs in here. That is called the edge imperfection. And another one is in the 3-dimensionally. Sometimes the crystal are organized in such a way that it behaves like a screw. If you go this way and this way, it goes up. Okay, and that looks like an screw in 3 dimension. There is another plane comes in that region, and it creates the screw type dislocations. Okay, and that is called the screw dislocation for crystal imperfection. Okay, any question?
Sir, screw এটা বুঝিনি স্যার।
Or you did not understand the screw dislocation?
No, sir.
Okay, it's because when the in 3 dimension, I was showing the edge dislocation in here, like one single plane come into the region. But in this case, what happens that there is another plane comes when a single plane comes into that place. Okay, into that region, a plane is in there. But what happens is that the atoms are organized in such a way that because of the insertion of this kind of edge dislocation, the crystals actually organized in such a way that it does not maintain the whole plane. Okay, it becomes there are extra atoms present in this region. Okay, there will be extra atoms present in this region, and because of that, crystals are organized in such a way that this is a plane. Okay, this is a horizontal plane, and that is also an horizontal plane. And because of the insertion of let's say not the insertion of extra atoms, but I would say that because of the irregular atomic arrangement at the crystal grain boundary, the atomic distance between this bit increases in these atoms. Okay, the atomic distance increases, and suddenly a different type of plane is formed at a certain angle. Okay, and because of the formation of this angle, it behaves looks like an screw, and all the atoms organized in on top of this plane, okay, will be similar to this. Okay, and then the plane will be like curved. It will be a curved plane, and another layer of atom will be present in here. If you put another layer of atom in here, it will also organize like this. Okay, and that is why it's called the screw dislocation. That means one side is distorted. It was supposed to be a complete plane. Okay, with this, it was supposed to be. I'll show with a different color. So this. It was supposed to be a plane like this. Okay, it was supposed to be a plane like this, but because of these atoms in here, because of these atoms in here, it actually forms a curved plane. And all the atoms, when comes together with this on top of this, becomes similar to this plane. And the bottom planes in here, if you talk about the bottom planes in here, these planes are perfectly horizontal. Okay, these planes are perfectly horizontal, and it was supposed to be the planes were supposed to be like this. All the planes are supposed to be horizontal, but suddenly one plane of atoms come into here because of the imperfection, and then all other planes on top of this will be arranged like this curved plane. Okay, and that is why it is called the screw dislocation.
বুঝছি স্যার।
Okay. Any more question? All right. So in the next class, we will be studying, we'll look at the alloy and its classification. And then after that, we'll go to the phase diagram, how the alloys are created and they become solidified.